All right, so here is our first example of a work done by a force that's variable. So we have in this figure an 8-kilogram block slides along a frictionless floor as a force acts on it, starting at x1 equals 0 and ending at x3 equals 6.5 meters. So we know the mass is 8 kilograms. As the block moves, the magnitude and direction of the force varies according to the graph shown to the right. For example, from x equals 0 to x equals 1 meter, the force is positive in the direction of the x-axis and increases in magnitude from 0 to 40 newtons. And we can see that right here, right? This is from 0 to 1 meter, and we're increasing in magnitude from 0 to 40 newtons. From x equals 4 meters to x equals 5 meters, the force is negative and increases in magnitude from 0 to 20 newtons, which is right here. Note that the latter value is displayed as negative 20 newtons. The block's kinetic energy is x1, at x1, which is here, is equal to k1, 280 joules. What is the block's speed at x1 equals 0, x2 equals 4 meters, and x3 equals 6.5 meters? So we know that we have a graph of force as it varies with position. So because of that, in order to get the work done by this force, we're going to look at the area under the curve. Now, the reason that we want to look at the area under the curve instead of just taking an integral is because, number one, we're not given how the force varies as a function of time, like the equation for force. But do you see how this graph right here, it's very linear, right? We have a linear increase from 0 to 40 newtons here. We have a constant force from 1 to 3 meters here, and then a linear decrease, a linear decrease. So because of that, it's easy to find the area under the curve. So when you have something like this, and we're going to have to find the work done on the object, because in order to find the change in kinetic energy and therefore the speed at x1, x2, x3, we're going to have to find the work done on that object, okay? Now, first and foremost, we know what the kinetic energy is at position 1. So because of that, and we know the mass, we can already find the velocity at position 1. So we can do that right away, and then we will find the work done on the object. So at position 1, we know kinetic energy at that position is 280 joules. And then if we want to know the velocity, not initial, the velocity, then we can use kinetic energy is equal to 1/2 mv squared. So solving for velocity here, we get 2k divided by m, square root of that, square root of 2 times 280 joules divided by the mass, 8 kilograms. And so we get 2 times 280 divided by 8, square root of answer. We end up getting 8.37 for the velocity meters per second for the velocity at position 1. So now that we found that, then we can find the work done in order to find the velocity at positions 2 and 3. So if we look at if we look at that graph right there, we can see here that we're finding the work, well, we're going to find the velocity at position 2, which is 4 meters, which is right here. So we can see that from 0 to 4 meters, we have a positive amount of work being done on the object because we have a positive area under the curve. It's above that x-axis. So because of that, all we want to do is first, we know that work done on object equals the area under the curve. And so in order to do that, what we need to do is we need to look at that curve and we need to split it up into segments where we can find the area easily. So I'm going to draw that curve really, really quickly. So I can see that this is 20 and 40, and then we have a negative 20, and this is the force on the y-axis. And then I can see that I'm going by 2, so 2, 4, and then 6. and then that'll be 7. So we can see we're going at 1, we're going up to 40 here, and then to 3, and then back down, it looks like. Yeah. So like this, and then like this. And then from 4 to 5, we go down to 20. And then we go to 6, and then it looks like 6.5 is when we come back to 0, like this. Oops. Let's do that a little bit better. Okay, so the first one, so this is our position 2, right? And so we need to find the area under the curve here. Now, in order to do that, I'm going to split this up into 2 triangles and a rectangle. So here we can see that we get, I'm going to call this work 1, no, we'll call this area 1, area 2, and area 3. And so the work done from x1 to 2 will be area 1 plus area 2 plus area 3. So we get work done from 1 to 2 will be equal to area 1, which is going to be 1/2 base, which is 1, times height, which is 40, plus area 2, which is just base, which is 2, times height, which is 40, and then plus 1/2 base, 1 times 2 height, which is, again, 40. So we get 20 plus 80 plus 20, and that's going to equal 120 joules of work being done on that object from that position 1 to position 2. Okay. Now for this, the next thing we want to do is, remember, our goal here is to find the final velocity at position 2. So we know from the work kinetic energy theorem that work is equal to change in kinetic energy. So this will be the work done from position 1 to position 2, and that will equal the kinetic energy of position 2 minus the kinetic energy of position 1. Now we already know that the kinetic energy at position 1 is 280 joules. That's given in the problem. And so all we need to do here, because we already know the work as well, we just have to plug in our kinetic energy equation for kinetic energy at position 2 in order to find the velocity. So I get work from 1 to 2 is equal to 1/2 mv2 squared minus kinetic energy at 1. Plugging in some numbers here, we get the work 120 joules equals 1/2 times the mass, 8 kilograms, times v2 squared, minus the kinetic energy at position 1, which was 280 joules. So here I'm going to add 280 to both sides. I get 120 plus 280. So I get 400 there, 400 joules. And that equals 1/2 times 8 times v2 squared. So 400 divided by 4, and then take the square root of that, and we get a velocity 2 equal to 10 meters per second. Right, so that's our velocity at position 2. All right, to now find the velocity at position 3, which is 6.5 meters, we need to first find the amount of work that's done from position 2 to position 3. So that, if we look at this graph again up here, we can see that if we divide this up, because again, finding the work means that we have to find the area under the curve. I'll call this area 4, area 5, and area 6. So we can see 4 and 6 are both triangles, so we get 1/2 base times height, and then area 5 is a square or a rectangle, so it's just base times height. So for area 4, it's 1/2 times base, which is 1, times the height, which is a -20. So I get, this is area 4 plus area 5 plus area 6. So we get 1/2 base times height plus area 5, which is base, which is 1, times height, -20, plus area 6, which is 1/2 times 1/2, which is our base, times the height is -20. So 1/2 times 1/2 is 1/4. So we end up getting here a negative 10 minus 20 minus 5, which is negative 35 joules for our work done from position 2 to position 3. Okay, so in order to find the velocity then at position 3, again, we can use the work kinetic energy theorem. So we'll say, okay, the work done from position 2 to position 3 will equal final kinetic energy, which is the kinetic energy at 3, minus initial kinetic energy, which is the kinetic energy at 2. Now, I don't know what the initial kinetic energy at 2 was because I didn't solve for that. I solved for velocity, but I can just use the kinetic energy equation, 1/2 mv2 squared for that. So we get work done from 2 to 3 is equal to 1/2 mv3 squared minus 1/2 mv2 squared. So now we can plug in our numbers. We get a negative 35 joules equals 1/2 mass, 8 kilograms, times V3, which is what we're solving for, squared, minus 1/2 times 8 kilograms, times V2, which we found to be 10 meters per second, and then square that. So we get negative 35, and then we're going to add 0.5 times 8 times 100, because 10 times 10. And so we get 365 for that. 1/2 times 8 times V3 squared. And so I'm going to divide this number by 4, 1/2 times 8, and then take the square root of that, and we get a velocity at position 3 is equal to 9.55 meters per second, which makes sense because we do negative work on this object, thus taking away some of that kinetic energy and slowing the object down.